So, yeah, I think it is time and we can begin. Um, before we begin, Agri, I think you had something to say. You could please share it. Your volume is a
Can you hear
little
me?
your volume is a little low. I can't hear you well.
How about now?
Yeah, that's fair.
Hi. Yeah, I guess about the experience on Saturday.
Yes.
Yeah, I can say it was really a nice event,
Okay.
manageable, and got to see a number of people that I've been seeing online, like Snoopy, and we talked a lot with them, shared their minds, shared contacts, connected. So it really made a sport building and exploring the free space. And
Okay.
I'm really grateful to be part of this cohort. Everyone that is in here is really glad I've been able to get you. That's what I have to say.
Okay, yeah, I think that is helpful feedback. Yeah, unless there's someone else with something to say, I think it is just the best time to start talking about layer 2 scaling solutions. So, this is going to be a more interactive session. So, if you have anything you know about layer 2 scaling solutions, I'm going to just share my screen in a few. Uh, but yeah, you could tell us, uh, Mwanje Ronnie, what do you know about scaling solutions, layer 2 scaling solutions? By the way, I'm going to be typing most of the concepts in the Rise Up pad that we have, the Decentral Code Rise Up pad. Yeah, let me just share my screen now. As Mwanje, you gave us some feedback. Yeah, what is a layer 2 scaling solutions in your own words?
Okay, I think layer two scaling solutions are simply layer twos built on certain blockchain that scale it. Usually, they are trying to solve a problem of scalability
Okay.
by tackling either time it takes for one transaction to go through all the gas fees. So usually they have some sort of protocol that either somehow bypasses the gas fees or improves the speed of the transaction.
Okay. Yeah. Paul, could you please give us something? Okay. Share something about layer 2 scaling solutions. Paul Damba. Okay. Yeah, I think he's not sharing anything. So today is 2025. Today is 11th. And by the way, to the ladies in this session today, we apologize. We forgot to wish you a happy Women's Day, and I'll take the opportunity right now to wish all the ladies a happy belated Women's Day. We appreciate you and we cherish all of you. Judith and who else is here? Oh, just Judith. Thank you for being determined and resolute to learn Web3. Yeah, so essentially, just like Ronnie had said, today we'll be looking at layer 2 scaling solutions. And I'm going to try to explain it from this concept that I believe we're all familiar with, the blockchain trilemma. So, the blockchain trilemma is simply a phenomenon in the Web3 space. I hope we're all clear. Is there any? I hope you can. Oh, sorry, my. Can you all hear me now? Some thumbs up, please. Okay. So, I'm going to be explaining layer 2 scaling solutions from a concept that I believe we're all familiar with, the concept of blockchain trilemma. Uh, what essentially that is a combination of challenges that have remained formidable in the blockchain space and that are very difficult to do away with all at the same time. So when one of them is being solved, it compromises solutions on the other. And these constitute decentralization. So I'll be explaining each of these in a way that I believe should bring them out more clearly, give them more clarity on why layer 2 scaling solutions are important. So there's a problem. One of them is decentralization. The other is performance, or which has been popularly known as scalability. And the last one is security. So each of these three, you're welcome, Angela. So each of these three issues in the blockchain space has remained elusive to all the technologies in the Web3 space that have evolved. If one of them is achieved, has been solved successfully, the others seem to be compromised. And we're going to see how each of these presents a challenge on the improvement and consistent enhancement of blockchain technology. So decentralization, in essence, is simply existence, this is in my own words, of a distributed network of computers operating on the same protocol. So it's mostly like we have computers all around the world that are running on instructions that are exactly the same for each of them. So for performance, essentially it's about how fast a blockchain can execute computations for even an increasing amount of inputs. So this means that if we have about 100 transactions that are requesting to be executed, if this number increased to about 2,000 transactions that are requesting to be that are requesting to be finalized on the blockchain should be able to, almost at the same level of efficiency, execute all those transactions. So that means if it was able to execute 100 transactions maybe in a second, it should relatively be able to execute 2,000 transactions in the same period of time. So that is what essentially scalability is looking to achieve. But because of issues with computing power, and other dynamics that control how blockchains finalize their transactions, these transactions have to be prioritized based on certain features that they constitute. So, for example, if we have maybe 2,000 transactions, for instance, not all of them can be processed at the same time. So there has to be a criteria for choosing which transactions are going to be executed before others. And that's where the element of gas fees then comes in. And then for security, this is simply about ensuring that the transactions are finalized in an immutable way. So that means that when there's a validation process going on for these transactions to be put on the blockchain, when they are registered in such a way that they cannot be changed. That the solution that has been, the result that has been put on the blockchain is final and immutable. Now that's where security is also a factor to consider in the blockchain trilemma, and we're going to see how each of these interplay and how layer 2 solutions come in as a solution to try to create a balance between all these problems. So in the case of decentralization, for a blockchain to be authentically decentralized, it needs to be distributed among people. That essentially the purpose of decentralization is to make sure the blockchain transactions can be validated and finalized without there being any chance of compromise. So the smaller the number of people that are required for a transaction to be complete on a blockchain, the higher the risk of it being compromised. So if we have maybe 5 people that validate transactions on a blockchain compared to 2,000 people, maybe 5,000 people that validate transaction on a blockchain, from all these, from these two comparisons, we can clearly tell that when there are less people involved in the validation process, there's a high chance that the transactions can be compromised and modified according to the requirements, to the needs of only these 5 people. But when there's an increased number of people, when there's a high number of people that are required for transactions to be validated on a blockchain, now in the case of these 5 transactions, if these 5 people agree, it is possible that they could modify the data that has been stored on the blockchain. For those that have been in the blockchain space for a while, I think you've heard of the 51% attack, where for the transactions on a blockchain or for the state of the blockchain to be modified, it only requires at least 51% of the nodes to agree that the state of the blockchain is not authentic and requires certain modifications. So when the number of nodes on a blockchain increases in number, there are lower chances that a blockchain is modifiable or compromisable. So that means that the data that has already been stored on the blockchain has immutably and safely, securely been stored. Now, why decentralization is a problem? Why it's part of the elements in a blockchain trilemma is that for a blockchain to be decentralized, to be widely decentralized, it needs to lower its security. By that, what I mean is that, for example, if Bitcoin was being very secure, in the sense that it required a very tight security, so many security protocols for a transaction to be proved. Maybe the transaction had to go through a layer of about 17 security layers, 17 security measures for it to be validated, which would require them to be computations, of course. It would be very difficult for so many people to have the capacity to run a node on Bitcoin. Let me just try to demonstrate it here. If we have high security, now I'm looking at decentralization and why it's important, how it impacts security. If we have high security, this implies, let me look at a hypothetical value of maybe 17 security proofs for each transaction. It's just a hypothetical value, doesn't represent anything, but I'm simply demonstrating the concept of high security. Imagine if you are getting into a building and you had to go through about 20 checkups for you to get into a building. That would require that for people to get in at the same rate as they would if the security was low, there needs to be more entry points. Hypothetically, that's what I would imagine. So if we're going through one entry point to get into a building, and we're going through, you're welcome, Maria, So if we're going through if we're going to enter a building and we have one entry point which has a high security, we're definitely going to be delayed to get into the building. But if we have the same level of security and we have about 30 entry points with the same high level of security, then we may get in relatively much faster than if the same level of security was deployed on one entry. So now we have 30 entry points with one rather with high security, and the entry is faster than when we have one entry point with high security. You're welcome, Teddy. So for us to scale, let's say each of these security points was being managed by an individual. Perhaps security companies, let's say, not everyone may have the capacity, not every security company may have the capacity to establish and institute that kind of high degree of security. Maybe some may not. And that now starts to limit the ability for people to be established in that place, maybe in that building, as security entities. So you may have, instead of having 30, because only 5 people have the capacity to establish that kind of security detail, only those 5 people will be able to institute the security detail, maybe at the building. And what that means is that if these 5 people agreed on something that could compromise the overall security of the building, they can agree on it, and it will affect the authenticity or maybe the safety of the people that are entering the building. So, in the same sense, by the way, I hope that analogy brought out the concept clearer. I was thinking of how to make it clear. At least give me some feedback, or I could clarify it further. Hello. Okay, thank you very much. Now I'm going to get back to the concept. So when I use that analogy and bring it back to decentralization and how it impacts security. So the higher the security detail that is required for the computations that are required for a transaction to be proved as valid and for it to be finalized on the blockchain, the more computations that are required for that to happen, the harder it becomes for people to afford the, the computing power to be nodes on the blockchain, on a particular blockchain. So that's the same reason why we don't have nodes in Uganda here, because we don't, not okay, maybe we do, but not so many people are able to afford nodes for certain blockchains. For example, for running a Bitcoin node, you may be able to run a node for maybe an L2 because the computing power that it requires for you to validate a transaction on that blockchain is not as much as it would require for you to validate a transaction on the Bitcoin network. So up to this point, I know at least that running a Bitcoin network is resource intensive. You need high compute. You need okay. Yes, Ronnie. Hello, Ronnie. You raised your hand.
Sorry, I thought I was unmuted. So I was wondering on
Yes.
the issue of running a Bitcoin node.
Hmm.
When you say that it is resource intensive, does it mean that I can't run it on my PC, or even if I run it, I will not be able to verify transaction? What do you mean resource intensive? Because for me, I was thinking all along that I can run it if I wanted to
Okay.
verify there.
The truth is, running a Bitcoin node on your machine may not be very effective. Either it will affect how fast your machine runs, or it will break down your machine. Because I don't know how best to explain this, but computations on the Bitcoin blockchain require a lot of processing power. I think we should perhaps do a little bit more research about this. But it's very difficult for you to run a Bitcoin node on your machine. It cannot sustain the rate of transactions, first of all, and the computing power it requires for a transaction to be validated on a blockchain, on the Bitcoin blockchain. But not all blockchains require that much computing power. There are some you can run on your machine. I know some that I'm personally thinking of running on my machine, or you could even run one on a virtual private server. But that's a subject for another day. I hope I was clear. Yes, Ronnie? Some feedback, please. Okay. Yeah, actually, for things like, okay. Yeah, we can discuss that later. So yeah, I was simply demonstrating the concept of how high security can impact capacity of people, how a high security on a blockchain can impact how many people are able to afford being able to run a node on that blockchain. So the higher the security, rather maybe the higher the computing power it requires for a transaction to be proved and validated, the more, yes, the higher the computing power, which word can I use? The higher the computing power it requires for a transaction to be validated on a blockchain, the fewer people can afford to run a node on that blockchain, because it would require that they have a lot of machines and that they are consuming a lot of power. And that means it's going to be left in the hands of the few people who have the money, who have the capacity to run nodes. And when that happens, it will reduce the ability of the blockchain to be decentralized, and it will be left to the few people that are able to run a node. And then, when those people are few, there's a possibility that they can compromise the integrity of a blockchain, because they can come to agreement. They're just a handful of them. They could even just have one Google Meet and agree on something and then modify a blockchain. So for a blockchain to be authentically decentralized, it needs to lower the level of security it requires for a transaction to be validated. So in this case, we're going to see how all this impacts the other. So the lower security, the highest low security. In this case, maybe we have two security proofs, two authenticity proofs. Maybe I should use authenticity in this case. These are just all things I'm using as analogies to help you understand the concepts I'm explaining. Yeah, maybe validation should actually be the word. Two validation proofs. Ronnie, don't laugh at me. I'm trying to make this simple. Okay, so when we lower security, we lower the computing power required for a transaction to be validated, and then also we lower the entry requirements for people to run nodes on that particular blockchain. So that means that more people now can run nodes on that blockchain, because it's the amount of resources it requires for someone to run a node is affordable by a number of people. And so many of these blockchains exist. There's one I'm particularly trying to get into running. It's called LivePeer. What it does is simply transcoding videos using it's actually a DPIN. I don't know if you know what DPINs are. Does anyone know what a DPIN is? Mwanje, please tell us, what is a DPIN? You're quiet. I would love to know. Okay.
Okay, the pin, let me see, is a decentralized physical, is it physical network or physical infrastructure, something like that. So all it is like, it's like, it's a decentralized, it's a decentralized service, sort of. It's like providing storage, but in a decentralized way, like Filecoin and other protocols there.
Okay, thank you for your submission. So what a DPIN is essentially is a decentralized infrastructure that utilizes personal resources, your personal resources, to achieve a certain purpose. So if you connect to a DPIN, if you connect your computer to a DPIN, your personal computer to a DPIN, it's supposed to achieve the purpose of that DPIN. Maybe it's going to utilize your processing power. So what LivePeer does, it uses your graphics processing unit to transcode videos that are going to be deployed on some decentralized version of YouTube. So that anyone that is in even the lowest bandwidth is able to watch videos without them buffering. So that's the purpose of LivePeer as a DPIN. Other DPINs do other things. Some utilize your internet, your bandwidth that is unused. One of them is Grass. It's a Solana project. And there are quite a number of them. But the concept, yes, Maria.
Is it the same as the? Okay, are you trying to say that it's a decentralized pin or a digital pin?
Sorry, I didn't get your question clearly, please.
Like, is it a decentralized pin or digital pin?
No, DPIN is just a short form for a phrase. Actually, let me just put it here so that we all see it. This is what it is. So a DPIN is a decentralized physical infrastructure network. It is not a PIN like a personal identification number, the ones we use for security in different applications. It is just a network that is decentralized and uses resources of nodes to achieve certain purposes, certain things, certain let me say computations. So, like the example I was giving, it is supposed to transcode videos, but it uses when you connect on that network, it uses your computing resource to transcode videos. And there are so many others that do different things. Some monitor weather data, so maybe you could connect your watch to a DP network, and as your watch traps weather data from around you, it is stored on that blockchain and it's used for some other things. Yeah, so essentially, I'm trying to paint the picture of a blockchain that doesn't require a lot of processing power, that you can even run it on your personal resource, on your computer, on your phone, to serve a particular purpose. Now, that is what decentralization is, that it can be affected by how much security is required for data to be validated. So for applications, rather for blockchains like the pins, which can run on our machines, when data is taken in, it doesn't go through very rigorous processes of validation for it to be finalized or be taken in and recorded. So that makes it easy for our machines to be able to run it, and that means so many people around the world can run it. And when that data is collected and immutably stored, since we are so many around the world that are running nodes on that particular blockchain, it becomes hard for someone, a single individual, or even a handful of people, to attempt to modify that data because it requires validation from so many people around the world and it is very difficult to achieve. So, the lower the security, the higher the possibility of decentralization, and the higher the security or the higher the validation process, the lower the possibility of validation because of the concept of how many people can afford to run a node on that particular blockchain. So I hope the relationship between decentralization and security is very clear. And then for performance, I think for performance it's really about um, the process, the process of validating a unit transaction. So in cases where we have to validate a single transaction at a time, but maybe even in proof of work, because rather proof of stake. So we have Ethereum. In this case, it's the one that we're actually going to be looking at as the base layer, and then layer 2 solutions built on it, and then maybe other blockchains. So the consensus mechanism used by the blocks by Ethereum is what? Someone please, I want someone to mention it. What's the consensus mechanism for Ethereum as a blockchain? How does it validate transactions?
I think it uses proof of stake, but as if it started with some proof of work and a
Yeah,
mixture of proof of
yeah,
stake, something like that.
it did start with proof of work and then advanced to proof of stake. But maybe help us understand, what does proof of stake mean?
So it's a consensus algorithm
Okay.
that based on your stake really, on what you are staking, proof of stake.
Okay. Yeah, I think that
It's
is
like proof of work.
okay.
You are validating transactions with your physical resources. Now here you validate depending on your stake. So
Okay, that's clear. For us not to digress and go into so many other things, I will focus and take his definition. So it's essentially okay. Now for Ethereum, the consensus mechanism is proof of stake, and it is theoretically faster than proof of work. That means transactions. It can deliver more transactions on chain in a second, more than proof of work, faster than proof of work. So the hypothetical amount of transactions that can be proved in a single second in a proof of work consensus mechanism. Let's look at it. Transactions per second. Okay. Anyway, I don't know what the actual value is, but for Bitcoin, I think there's a transaction validated every 10 minutes. Is it 10 minutes? Can someone clear this value for me? I don't think I remember it correctly. And then here we can have, I think, between 15 to 30 transactions every second. Am I right about that? For Ethereum. Okay. Thank you very much, Angela. So, what I wanted to explain further is this. Even with 15 to 30 transactions per second, it is not sufficient to accommodate how much activity is going on around the world. Because I think so far, from where we stand right now, I could say the Ethereum blockchain is the most active blockchain. Would you agree with me if I say that? Hands up, please. Some feedback. Anyone that contends my suggestion, my opinion. Some hands up. Maybe just remove your unmute. Thank you very much. Okay, so is someone saying something? Okay. So essentially, even with all these transactions in a single second, it is not sufficient to accommodate the input, the throughput that is required for Ethereum to be effectively scalable. Because so many people every single day are running ever increasing amount of transactions, maybe through decentralized applications or through their wallets that require the Ethereum blockchain to be much faster. But because of essentially how it operates, using the proof of stake consensus mechanism, it limits how far it can go in a single second. So with proof of stake as a consensus mechanism, it would never be able to accommodate a certain number of transactions in a single second, because transactions have to go through that particular process to be verified and stored immutably on the blockchain. And this is what I mean. For example, if we had maybe 2,000 transactions that are waiting to be processed, transactions that are waiting to be processed, Ethereum may not be able to process all these transactions at the same time. So what then would it need to do? It would need to prioritize what transactions to complete first and which ones will come after. So what is the mechanism it does by which it does that? It has to increase the gas fees. Rather, the transactions that have a high gas fees are going to be more priority. Transactions with high gas fees are of priority. And then those that have less gas fees will be completed later, after the ones with high gas fees have been processed. Well, the philosophy behind this is these transactions are supposed to be processed by the computational power of the nodes. So there has to be a mechanism by which some of them are put in a queue before others. Hypothetically, that is logical, because the blockchain may not be able to try to confirm all of them at the same time. To take it back to our analogy, just a moment, please. Yeah, to take it back to our analogy, if we had the analogy of a security line, a security detail at a stadium perhaps, if we all had to get into the stadium at the same time, but we have different kinds of tickets. Some have ordinary tickets, some have VIP tickets, some have maybe VVIP tickets. It would only be logical and considerate that the people that have paid more money to watch this match are given more priority. Maybe they even have a special entry point for themselves. So in the case where we have maybe 2 entry points and we're all getting in through the same entry point, for me to get in, and I paid maybe for the ordinary ticket, and then I have maybe 7 people that have paid for the VIP ticket, it is only logical that they go before me because they invested more money just to watch this match compared to me. So ideally, that's the concept with transaction prioritization when the transactions are going to be validated on Ethereum or even any other blockchain perhaps. So those that have paid higher gas fees, their transactions will be prioritized over those that have lower gas fees. Just like it would be only logical that those that have paid more money to watch a match go inside first, and then you who have paid for ordinary seats come in later, because your seats may not even be indefinite positions, but those that have paid higher maybe have their seats already waiting for them, and it's just the security process that is delaying them. Yeah, I hope that concept is clear of how gas fees increase as activity increases on a particular blockchain. So the process by which transactions are verified on Ethereum proof of stake still has a limitation. There's a certain number of transactions it cannot contain in a second. And that is why we needed layer 2 solutions. Layer 2 scaling solutions. And what layer 2 scaling solutions are? They're simply independent technologies. Maybe, let me say this, independent blockchain technologies that increase the throughput of a particular blockchain. In this case, if we're looking at Ethereum, so what throughput is, okay, we're going to look at it. Let me first finish the definition. So there are independent blockchain technologies that increase the throughput of a particular blockchain while also minimizing the transaction cost. So just to explain that definition, give it more clarity. So essentially what throughput is a number of transactions. Okay, now amount of data, perhaps, let me call it, it's actually amount of data. Amount of data that is processed or received in a particular period of time. Now this is typically a second. So I'll take this perhaps to the data buses as we know it. Data buses as we know them in machines. So there are those that are 64-bit, there are those that are 32-bit. So a 64-bit data bus definitely carries more data in a single second than a 32-bit data bus. So essentially, oh, thank you, Maria. Maybe you could tell us what you're most appreciative of. Okay, no feedback. So what essentially what a data bus, what throughput is how much information can go through this particular channel in a particular second. Now that there are so many variables there, it depends on the size of the channel, depends on the mechanism by which data goes through the channel. Now, to put that in the context of blockchain, the mechanism by which data is processed on Ethereum as a layer 1 cannot sustain a certain threshold of data, a certain threshold of transactions. So it would require that a different mechanism is deployed for it to be able to contain more transactions in the same short time. That is why layer 2 solutions come in handy to increase how many transactions Ethereum can execute in a particular second. Or yes, in a particular second. So throughput is simply amount of data that is received or processed in a particular period of time, typically a second. And then minimizing the transaction cost. We're going to see that practically, but that means that we're simply actually minimizing gas fees. So that's what layer 2 scaling solutions do. That they increase the performance, because performance, as we said it here, is how fast the blockchain can execute computations for an increasing amount of input. Now with a layer 2 solution, as the increasing amount of input, as input becomes ever more increased, layer 2 solutions are able to contain that information and process it in relatively the same time that it would require to process transactions that are fewer. Is that clear? Thumbs up or some feedback, please. Thank you, Ronnie. So, okay. So, now layer 2 solutions have a number of technical, I wish I could open a new one. Can I? Okay. So layer 2 solutions. Okay. So Layer 2 solutions have four mechanisms, or four types so far that exist. We have rollups, and we shall look at them in detail. We have side chains. Okay, we have rollups. We have channels. Oh, she's in spelling of channels. We have side chains, and we have, who knows the fourth? There are four layer 2 solutions. Anyone can.
I think ZK. Is it ZK? I
Oh,
don't know.
okay. Now ZK is a subtype of rollups, and then channel side chains, and okay. When I remember it, I'll put it. Unless there are any questions, I would love that we take a break at this point, and then continue from there in at 6:10. If that's okay, please raise your hand if you would love that we continue just now. Just unmute your mic and tell us. Okay, I'll take the silence for a yes. So we shall resume at 6:10, at year 18:10. Okay, so see you at 18:10. Hello, Tracy. Grandma. Ma, yeah. Yeah, it's plasma, yeah. Plasma chain. Ma. What? Validium. So we change that things in the foundation. Just in. 6:10.
Nimetoka online, maybe they want to go through which account I will use.
No, we shall go through them again.
No, shall which account? And are you dating? No.
No, I'm just in 3 months talk, so I'm just looking at it.
No.
No, I don't know, but I have an idea, so I'm looking at it.
Otherwise, you're doing a good job. Keep it up.
Thank you.
Yeah. Recently, didn't tell people to register and write them.
Yeah, I think I could do that when we get back. No, it isn't. You have 1 minute to go. To know you. Okay, are we all here? Someone raise your hands, let me know you're here. Thank you, Ronnie. Agre, are you here? Agre? Oh, thank you. So we're going to look at each of these different layer 2 scaling solutions one by one and understand what each of them is in detail. So I think the fourth that I hadn't talked about is what they call a plasma chain. Someone reminded me. And plasma chain. So I think we should all register here, up, right here. If you can all access this Rise Up page, please put your name and Twitter tag like Maria has done here. Thank you very much for representing Maria. So yeah, I would love that we all do this. Put your Twitter tag there. Yeah. So that we can follow you, see what you're working on. Yeah, it will be very helpful. Thank you, Agree. Okay, so as people register, let's move forward. So what a plasma, okay, let me start with a roll-up because they're the ones that are the commonest. So earlier on, Ronnie was telling us of a ZK snack. And like we're going to see, there are two types of roll-ups. There are those that are called validity roll-ups or ZK snacks. And we shall look at this in detail. Actually, we're going to start with those. And those that are called optimistic roll-ups. Someone give me an example of an optimistic roll-up. Any example of an optimistic roll-up?
I think base, Lisk.
Yeah.
I don't know.
Yes. Base and Lisk are optimistic roll-ups. So maybe a validity roll-up. Someone give me an example of a validity roll-up, if you know any, before we understand how they operate and how they scale Ethereum and maybe any other layer 1 blockchain.
I'm just trying, I'm not sure.
It's okay.
Is Stacknet part of them?
Yes, Stacknet is a validity rollup. You are very correct, Ronnie. So let's start with validity rollups and understand ZK snacks. Let's understand what they are. Oh, sorry. Just went back up. So what a ZK snack is, let me first type it here. First of all, this word stands for a particular, it's an acronym. And I'm going to explain it word by word. So that's when you start to define what a validity rollup, it's very clear from its name. So this is word is zero knowledge. Succinct, non-interactive, argument of knowledge. Just to divide it in a way that makes it understandable, I'm going to divide it into 3 parts, I think. So argument of knowledge, non-interactive, zero knowledge, succinct. There are 4 parts actually, I think, for us to understand it better. So let me put it down here. So what zero knowledge in this case means is that the base layer, in this case, the base layer, okay, let me say the base layer doesn't receive a copy of the transactions. So that means when a ZK Snack or validity rollups does its processing, its transaction processing, the base layer does not receive a copy of the transactions. So in that case, there is zero knowledge. So the base layer has zero knowledge of the transactions that are being finalized on itself. So that means all the information about the transactions that are being executed remains with the validity rollup, or in this case, okay, just for as an example, remains on Stacknet. Yeah, that's what zero knowledge means in this case, that the base layer does not receive a copy of the transactions. But what is called a validity proof. So simply what that would mean is that it receives only information that validates that the transactions that are being finalized on it are authentic. So it only receives that piece of information that suggests that all the transactions that have been finalized in that particular period or in that particular batch are authentic. Am I clear? Is the concept coming out? Some feedback. Okay. So succinct simply means that succinct in English simply means precise. Precise, simple, precise. Now, in the case of a ZK Snack, succinct would mean that only the necessary information. Now, all these words find their definition in relation to the base layer, in this case Ethereum, compared to the validity rollup, which would be like Stacknet for, yes, which would be like Stacknet. So succinct means that only the necessary information is delivered to the base layer. The base layer, which in this case would be Ethereum. And that information is a validity proof. And yeah, I think that's it. Now, non-interactive. I hope that is clear so far. We understand what zero knowledge means. We understand what succinct means. We understand what non-interactive, maybe I'm going to define it now, and what argument of knowledge means. So what we're saying here is that for a ZK Snack, we say a ZK Snack is the full word is this. Let me actually type it here. Zero knowledge, succinct, non-interactive, argument of knowledge. Yeah, so say zero knowledge in this case means that the base layer doesn't get information completely about the transactions, but just the validity proof. We're going to see what a validity proof is. And succinct in this context means that only the necessary information is delivered to the base layer. So the base layer does not need to know about the transactions, but only a proof that these transactions have been executed and are authentic. So that particular proof that verifies, that validates the information, that validates the transactions, is all that needs to be delivered on the base layer, which is called a validity proof. And that is where the word succinct comes in the definition, the definition of a ZK Snack, that only necessary information is delivered to the base layer, which is in this case just the validity proof. Now, non-interactive, this simply means the base layer doesn't. The base layer in this case is verifier. What a verifier is someone who has to prove that something is true. So the best layer, who is the verifier, does not have to run further validation computations to validate the proof. So in this case, what this means is, to validate the proof submitted by the rollup, or which is also called a prover in this case. So the prover is simply a layer that confirms or validates transactions that are going through it, to confirm if they are actually authentic transactions that need to be executed on the blockchain or stored on the blockchain. So that's what the prover does. When transactions are going to be taken through it, it proves that they're actually authentic and then deploys the transaction data on the blockchain. Then the verifier is simply the base layer to which the proof that these transactions exist and they're authentic, to which that proof is delivered, which in this case would be Ethereum. So the base layer is a verifier, and in the case of ZK Snack, when that proof is delivered, it does the verifier does not have to, the verifier or the base layer in this case, does not have to run further computations to prove if the validity proof is actually also authentic. Because we had transactions that were processed and the validity proof was delivered by the layer 2 to the layer 1. And then the layer 1, when it receives the validity proof, that is final. It puts all the trust, computationally, it puts all the trust into that validity proof to be authentic. It doesn't have to run further proof mechanisms, rather further proof computations that this validity proof is also authentic. Now that's what it means that a ZK Snack mechanism is non-interactive. Like, the verifier doesn't have to continually interact with the prover to check if the information they have of these transactions is authentic. They trust that the prover has credibly done their job and delivered a validity proof for transactions that actually exist and that have securely been deployed on the blockchain. Does that make sense? Does it make sense? Okay. Yes, Ronnie.
How is this? How is this inter what? How is this established? How does the verifier trust the prover that the transaction will be true? How
Okay.
is it established? How is it implemented?
Well, it's simply implemented through. Now, layer 2s are built by Web3 developers, and the mechanisms with which these platforms have been built is already tested before they are deployed on their mainnet or before they establish blockchain networks. So, layer 2s and layer 1s, in this case for Ethereum ecosystem, they have a communication mechanism that has already been tested and proven. So because already by the fundamental nature of blockchain is that when data is deployed, it is immutable. So for example, for Stacknet, blockchains first of all are designed to be trustless, like we've always known. So for Stacknet, before it went to mainnet, the mechanism by which it verifies transactions, of course, was tested. And how it delivers proofs to Ethereum was obviously also tested before they went to mainnet and before it was accepted as a layer 2 solution for Ethereum, as a validity rollup for Ethereum. So the mechanism that was first tested and confirmed that it delivers transactions credibly to Ethereum is the same mechanism it uses now. And as we know, a blockchain has a mechanism of communication that enables immutability of data. So that means when data has been moved through Stacknet and its security features like they were already established, when all that data has been processed and delivers a validity proof on Ethereum, that whole process has already been established as reliable and trustless. I don't know if, I didn't want to go into technical parts, but I don't know if that makes sense. That all these systems are already tested before they can be thought of as reliable.
So what you're trying to mean, these are they like standards? Because
Yes,
my question is, what if I build something on top, then it sends fake transactions, like I control it and then it sends fake transactions to the base layer?
uh,
How is
now,
that
yes,
safe?
I get your question. So, for you to build a layer 2 solution that is reliable by Ethereum, I don't know what the standards are particularly, but there's of course a process that you have to get through. Maybe we should take time and look that up, but uh, I don't know how best to explain this. But I get your question though. You're wondering how the validity proof from Stacknet as a validity rollup can be considered reliable on Ethereum. Is that the question? Where's the assurance that it's reliable? Okay. Yes, Maria.
Actually, may I have a question
Okay.
that is similar to, I think, Manze's?
Yes.
Uh, okay, what could be the role Ethereum mainnet plays in verifying the validity of transaction? In case of any, I don't know.
Okay. What Ethereum does is that when that validity proof is delivered, it is considered authentic and it's stored on the blockchain. So actually, what really happens in ZK Snacks, I'm getting ahead of myself here, but just to answer your question, what happens in ZK Snacks is that it generates Merkle trees for certain batches of transactions. You know what a Merkle tree is by now? Yes. So if we have about maybe 30 transactions, because what a rollup does, the actual meaning of the word rollup is that it creates batches of transactions. Let me just put it here. Transactions. Maybe if there were 30 transactions. So a Merkle tree is created for those 30 transactions, and then the hash of the root is delivered as the validity proof to the Ethereum mainnet. Is that clear so far? Yes. So if you wanted to verify that a transaction is actually registered on the blockchain or on Stacknet perhaps, all you have to do is access the hash of the root of that batch. And then it is possible, from how we covered how Merkle trees are generated yesterday, how we covered them. I believe you know that with the hash of the root, it is possible that you can get a single transaction in that batch. Am I right? So a root hash is delivered as a Merkle proof on the base layer, it is stored as proof that these transactions were executed and stored by the validity rollup. after verifying that these transactions are authentic. And the authenticity of these transactions is also verified by the standard consensus mechanism of the validity rollup. Like all the nodes in the rollup should agree that this transaction is valid and should be deployed on the blockchain. So if we have about 40 transactions that have gone through that process, they are batched together, and then a Merkle tree is generated of them before they are stored. And then the hash of the root of that Merkle tree is saved on the Ethereum blockchain. Have I answered your question? So what the Ethereum blockchain does in the case of validating if transactions are true is that it stores the proof that those transactions were actually executed on the validity rollup. It only stores the proof. Have I answered your question? Thank you very much. Yeah, and just to finish my definition, what argument of knowledge means in the case of a ZK snack, in the definition of a ZK snack, is that argument simply in English is simply evidence. So what I could actually change this to be evidence of knowledge. That's what it would mean in this case. So what's the evidence that the layer 2 solution actually has information about these transactions? It delivers that validity proof. That is the evidence that those transactions were actually processed on the layer 2 solution, and now it is delivering that evidence, that knowledge, that evidence of knowledge, that argument of knowledge. Argument of knowledge simply means evidence of knowledge. A single entity or a single unit of information that proves something. In this case, that information is proving that those transactions actually exist, that Merkle tree, rather that hash represents a Merkle tree of transactions that have already been deployed on the layer 2 solution. Is that clear? Hands up, please, someone. Nothing? Thank you, Ronnie. So, argument of knowledge. In this case, simply means the base layer. Okay. The L2 submits information. So the L2 submits information about the transactions it has processed in a single batch. L2 submits information. This information, in this case, everything rotates really around the validity proof. So the L2 submits information, which is a validity proof. Submits information to the base layer about the transactions it has processed in a single batch. So I hope that is clear. And we said this validity proof is actually the root hash of a Merkle tree of that batch. So you may be wondering, because if it's delivering only the proof, that is very small information. It is succinct, precise information about that batch. So just imagine you have all these transactions and hashes are generated of them, and only that one hash that represents the root of that Merkle tree is what is submitted to the base layer, to the Ethereum network in this case. That is very little information about all those transactions. So where are the rest of the transactions going? Now, what these rollups do is that they save the transaction data in maybe a central storage unit within the blockchain itself, but that is independent of the base layer. Or they could use an existing decentralized data storage service like maybe IPFS or Arweave. They save the transaction data on a data storage entity independent of the base layer. So in this case, what we're saying is, so it could be maybe a decentralized storage entity or data availability layer that is now in the case of Stacknet that is available to this particular layer 2, or that has already been designed to store that transaction data. So in the case of Stacknet, there's one called, I'm forgetting what it's called. Let me look it up. Just give me a moment. Just to demonstrate these things practically. Let me first start presenting and look for it. So unless there is a question, I can continue with my research on this. Please ask questions. Anyone? Maybe feedback on how far we're going. Is this being effective? Maybe feedback on how far we're going. Is this class being effective? Are you learning something? Or do I need to change the model of teaching?
I think the class is effective and it's good. I don't. You have said you are going to disconnect and search something.
No, I'm just looking for something here, but I'm really just giving us time to interact and see if try to all level and come to the same level before we move forward. Can you? I'm already doing what I wanted to do, so I just wanted us to interact. So if you have anything to add on, yes, Maria.
Okay, could there be any gas implications for the validity rollups on the Ethereum network?
Yes, there is gas fees involved, but it's reduced. So I'm trying to give you the mechanism of how a ZK snack operates, and we're going to see how that reduces gas fees and increases the efficiency of the layer 1 solution, of the layer 1 blockchain. So yeah, the data availability layer that Stacknet uses, of course there might be others for different purposes, and I'm using Stacknet because it's the one that I believe we're all familiar with, but there are so many other validity rollups, even in those other layer ones like Solana, maybe like blockchain, rather Bitcoin doesn't have so many, but it does have a layer 2 solution, and we'll look at it. So the data availability layer that Stacknet uses is called Celestia. I don't know if any of you have heard about Celestia. Is that a familiar term? Okay. So now, just to explain clearly what happens is, I didn't want to go through this, the macro root and all these things. I think we looked at all this yesterday. So just to save time, essentially this is what happens. When all the information has been processed, maybe for a particular batch of transactions, I could share this link so maybe you could understand how it works. I'm going to put this in the rise up. It's a data availability layer for Stacknet uses this, and so many other layer 2 solutions use it as well. So it provides a place where processed data can be stored. But you can generate Markov hashes, Mako tree hashes of that data that you've stored on Celestia, and then deliver the root hash on the main blockchain for which this data is on which this data is supposed to be stored. So that's what Stacknet does. It gets all these transactions, processes them, then generates a Mako root hash. Okay, generates hashes for all the transactions, and the root of that Mako tree is the root hash of that Mako tree is what is stored on Ethereum instead, rather than all this transaction data. So this transaction data is instead saved on Celestia, and then just the Mako root hash is what is saved on Ethereum. I think you can see now that the computing power that will be required to process those transactions if they were directly being executed by Ethereum has now been shifted onto Stacknet. Like there's an offload of computations that are now going to be executed by Stacknet, and the connection between Stacknet and Ethereum is that Mako root hash that is going to be delivered by Stacknet. Is that clear? Are we moving at the same pace? Okay, thank you. So, yes, Ronnie.
So is Celestia the same as Stacknet? What is Celestia with respect to Stacknet? Are they
Okay,
partners?
Celestia is a data availability layer. Now, what that means is that all the transaction data for all the transactions that are being processed by Stacknet. Now, that is the call data, maybe perhaps if you are storing a picture, maybe you have a gaming service, and you want to store all these NFTs with relation to your game somewhere. If you pass them through Stacknet, all that information, all that data is stored on Celestia. So Stacknet, there are so many data availability layers. So it's essentially, what Celestia is essentially a decentralized service where data can be stored. You know how IPFS works?
You are saying it's like an oracle. Is it like chain link or something?
No, Chainlink does a different thing. Okay, let me call it like a decentralized storage unit. You know how Google Drive works?
Yeah.
Yeah, so it will be like a decentralized alternative of Google Drive.
But it is specifically for Stacknet or any other chain can
No,
use
it's
it.
it's not for Stacknet specifically. So many other blockchains use Celestia. So it's called a data availability layer. Like it provides a place where data can be stored and make it available when you need it.
And it is decentralized.
Yes, and it is decentralized. You know how IPFS works?
Yeah.
Yeah, now this is just like IPFS.
So how reliable is it?
Uh, because it is decentralized, and at least by this point, we know how blockchains operate. Data is immutable when it is delivered, and that is the assurance of its reliability, that it is a blockchain network.
Okay.
Okay. I just wanted to put this link in Rise Up. I think maybe I'll put it here. You can look it up. Yeah. And see how it operates. Of course, it has its own protocols and how it accepts data, but we shall not go through that now. So what I wanted to say is when the transaction data, okay, it is stored somewhere independent of the base layer, and one of the services it uses is Celestia, Stacknet, and some of its tools. The design specifically for designing games, and well, you can't go into the Stacknet ecosystem now. Just for you to understand that this is how validity rollup operates. It stores data somewhere else, then only provides evidence of existence of that data on the base layer. Is that clear? So, basing on that understanding of how a rollup, particularly a validity rollup, operates, I won't look at optimistic rollups later. Let me just get this. Optimistic roll-ups. Okay, so basing on how we've understood how a validity roll-up works, this is essentially what it is. It batches transactions let me start with this. 1, processes transactions off-chain. By off-chain, in this case, I mean off the base layer. So in this case, in the Stacknet, on the Stacknet blockchain itself. So off-chain, by this I mean off Ethereum, perhaps. Let me be specific. Process transaction off-chain, batches transaction data 3, generates Marco tree, submits a Marco root hash to the base layer. So simply this is this is a whole process. So when transactions come in, they are batched together, they are processed. So a Marco tree, okay, maybe generates a Marco batches transaction data. Let me put it here as well. Let me put it here perhaps. This may not be the exact order, but I'm just listing the important parts of the process of delivery of processing data and deploying it on chain. Generates a Marco tree, set data in dependent. Availability infrastructure in an off-chain. Let me use off-chain in this case. Everywhere I use off-chain, just know I mean off the base layer. So it serves data in an off-chain data availability infrastructure and then submits the Marco root hash to the base layer as a transaction validity proof. So if you wanted to prove a particular transaction, existence of a particular transaction on the chain, all you have to do is get that Marco root hash and then use a Marco proof to verify, to validate if a particular transaction is part of the Marco tree. If you have the Marco tree, you have the index to the source, to the data source, then you can access the data. Simply indexing information and storing only the necessary information on the base layer. So how this whole process makes Ethereum, how this whole process scales Ethereum is this: it offload reduces computation power required to validate, to finalize the transaction. Transactions by offloading the transaction by offloading the transaction processing computations, perhaps. The transaction computations. So it reduces computation power required to finalize the transactions by offloading the transaction computations from the base layer to the layer 2. That means the transactions, instead of being processed directly by Ethereum, they are now going to be processed by Stacknet. That means there is more space now left for other transactions to be processed on Ethereum directly. That makes Ethereum more efficient. So all the computing power it would require for it to validate these particular transactions that are going to be delivered by Stacknet, it now has more computing power that is reserved for maybe transactions that have to be executed exclusively by Ethereum. Maybe someone is transacting Ethereum directly. Now, those are transactions that can only be proved by Ethereum itself. But there are certain things that these layer 2 solutions can do that will relieve Ethereum of the computational processes it would require for it to achieve certain computations. Rather, for it to finalize some computations. So the layer 2 solutions do that work and then only deliver a proof that they have done the work and confirm that these transactions are valid. Then they only deliver a proof to Ethereum that yes, these transactions are actually valid and here is the proof. So store the proof, and when someone wants to confirm if they are true, we have the data stored elsewhere. But if they have that proof, then they can validate that information and actually find the transaction data. So that's one way it does it. And then two, submission of the validity proof requires less gas fees compared to actual processing of the original transactions. So if Ethereum had to, since we're doing Solidity, by now you understand that every opcode constitutes a particular amount of gas fees for it to be executed on Ethereum. Now, imagine instead of delivering an entire smart contract, or maybe delivering an invocation of a particular function in a smart contract, and then just delivering data, a single piece of data, which is a validity proof in this case, which one would require more computation? Will it be delivering the data, the validity proof, or validating transactions in this case? I personally believe it would be delivering data, because it is just a piece of data you simply write into the blockchain. May not require a lot of gas fees compared to if each of these transactions was supposed to be processed one by Ethereum itself. Considering how active it is and how competitive it is to deploy a transaction on the Ethereum blockchain, it's going to require a lot of gas fees for certain transactions to be prioritized. But also, as activity increases, the gas fees also keep increasing depending on the demand on the blockchain. For those who have transacted on Bitcoin, I want us to look at something. Although there's a dynamic also, another dynamic that determines how much gas fees are required for a particular transaction to be verified. I want to look at the blockchain explorer for the Bitcoin network and show you something. Now, these are transactions that are running on Bitcoin right now. So I want us to look at the size of this. By the way, the size of that represents the size of the transaction. So let's look at two transactions here. Look at this particular transaction. The transaction ID is B5 something. It is an amount of 27 BTC, and the fee is almost $98. So now that's the gas fee. Let's look at something else. $98. And look at something that is much bigger. 98. When you look at these two, this and that, they're relatively the same size. But when I look at this one was $98 almost. Now when I look at this, you can see it is almost the same size. Although it is transacting a lower amount of Bitcoin. Yeah, no, that's actually meaningful. I wanted something that would represent the concept I'm looking for. How much was this? This was 27. 0.5. Okay. Okay, I don't think I'm seeing what I want. Let me just explain what I want to say here. So, okay. Submission of value requires less gas fees. So what I was trying to say is processing these transactions off chain would mean less computing power for the base layer, and that means the gas fees will be lower because the computing power that you're requiring to deliver a proof, just a single proof that certain transactions are true, and you're finalizing that proof on Ethereum, requires less computing power, so less gas fees, compared to those transactions being executed directly by the Ethereum blockchain, because it's highly competitive. Now, layer 2 solutions, most of them are designed to be architecturally less expensive. We won't look at the architecture of Starknet, but that is just a fact. They're designed to be architecturally less expensive compared to the base layer like Ethereum. So how they prove their data, how they validate information is technically different, computationally different from how Ethereum does it. And for instance, how they store data, even the base layer, even the L2s themselves, they don't store their own data. At least most of them don't. They store them in data availability layers. So you can see that there's a whole ecosystem of efficiency designed to make executions faster and less expensive for a user. Just like we defined them up here, we were saying layer 2 solutions are independent blockchain technologies that increase the throughput of a particular blockchain. So in this case, if Ethereum was supposed to run maybe 15 to 30 transactions in a particular second, because of Starknet, it can now execute more transactions in that particular second because it now has an extra computing power from Starknet that is running transactions and then validating that those transactions exist on Starknet. So now Starknet also increases the amount of activity that Ethereum can deliver, which is proved by the proof that these transactions, of course, are delivered by Starknet, or that are executed by Starknet on behalf of Ethereum. Essentially, that is the concept of scaling layer 2s. Transactions are run off-chain and proven on-chain. The proof of their existence is proven on-chain. The proof of their authenticity exists on-chain, in this case on Ethereum. So independent blockchain technologies that increase the throughput of a particular blockchain. Throughput is simply amount of information that is going through a particular computing service or computing infrastructure at in a particular second, typically. So the throughput increases and the gas fees decrease, like we've seen. Deploying a proof is much cheaper than running actual transactions. So that is how a ZK Snack operates, essentially. And all this that I've talked about is how it scales Ethereum. But the security of that proof is ensured by the security of Ethereum. We know that Ethereum is secure, and most of these layer 2 solutions, some of them are just starting up, and they're vulnerable to attacks because maybe they don't have a sufficient amount of nodes, and so many other reasons. But one thing is for sure, that Ethereum is secure compared to most of its layer 2s. So when there's a proof that is stored on Ethereum, the layer 2s are scaling Ethereum. They are increasing the performance of Ethereum, but still relying on the security of Ethereum to secure their transactions by just the existence of that proof. Because the data that proof validates exists somewhere securely in a decentralized storage, and as well, information about that proof also exists on the layer 2. I hope I made some clarity there on ZK snacks as rollups. Some feedback, please. Maybe someone has a question or something to add on or something to correct. I would love to receive that feedback. Arthur, you're welcome.
Thank you.
Okay. Okay, so we can move forward onto optimistic rollups. Now, the difference between a ZK snack or a validity rollup and an optimistic rollup is how they deliver the proof of existence of data. So, an optimistic, rather, a validity proof first validates data. First validates that the data is actually authentic before it delivers the proof. Now, what an optimistic rollup does is actually the opposite. It delivers the data, and then later, if someone that is checking the validity of that data finds a disparity in that data that can question its authenticity, then they'll raise a fraud proof. They'll do a fraud proof on that data to confirm if that data is actually true. And that is when validation can actually be made after a period of about 7 days. So it's like data is placed in some kind of probationary storage until someone can raise a query about that data. And that period usually takes about 7 days. Yeah, before we continue, I would love that we take a rest for a while. I need to take some water. So let's resume at 7:08. I think that is fair and respectful of each our time. Are there any questions at least up to this point? Yeah. Okay, are we all here? Some hands up. Okay, thank you, Ronnie. So let's continue. Yeah, I was looking at optimistic rollups as an alternative. Okay, no, yeah, maybe an alternative to validity rollups. So how these actually work is slightly opposite, slightly different from how validity rollups operate. When data is batched together, at least they have that in general. That's where they derive their name, rollups. They batch data or they batch transactions, just to be even more precise. They batch transactions into a single unit, but when they submit a state proof, like we looked at up here, they submit a state proof to the blockchain, to the base layer. The data is available for for proving if it is actually valid for a particular period of time before it can be finalized. So they are slower because they wait on someone that is inspecting that particular data set to confirm if it's actually valid for it to be finalized as authentic data. Now, because of that, what happens is it takes a lot of time, averagely a period of maybe even up to 7 days, at least that's what I've seen. A period of up to 7 days for that data to be validated, for those transactions to be finalized, because they are waiting on someone to submit a fraud proof. So the different, let me just write it here. These require of a for a batch of transactions to be proven. Now, this takes some time because the person that does the inspection may not exactly deliver their full proof immediately. It could come after days. So there's just a window within which that full proof should be submitted before that data can be finalized on the blockchain. And it's averagely up to about maybe 7 days for certain optimistic rollups. And I think many of us have experienced this with Binance, perhaps. You transfer some tokens from somewhere and deliver them maybe to your Binance wallet, and you have that window within which you can't even withdraw those tokens. They are available, you can see them, but they're not accessible to you for exchange because the data hasn't been finalized on the blockchain from which they came. Maybe from the wallet, maybe the transaction hasn't been finalized yet. So you have to wait until there's been finality in on that particular blockchain for you to be able to receive and have that money exchangeable. Or it could be data, it could be anything else. So they essentially use the same mechanism as a ZK rollup. The only difference is that the data isn't validated initially, it is actually validated later. So yeah, I think that is all about optimistic rollups. Unless someone has a question about them, I want to move on to channels. So optimistic rollups, I think we've seen a number. Here we're using the example of Stacknet, and here we have a number of them. We have Lisk, the one that is commonly known to us. We have Base. Yeah, and of course all these systems are being continuously improved, so some of the definitions we have of them right now may not be accurate in the future somehow. But at least where we stand now. Yes, Ronnie.
So on those two roll-ups, which one is preferred? Which one is the best? Which one should be like the better one?
Well, I won't say there's such a thing as the better one over the other. It really depends on the use case. If you're transacting things like money, like funds. Of course, you'd want something that is faster. Maybe you prefer to use a ZK snack, but if you're perhaps minting things like information on a piece of land, maybe you're tokenizing or someone wanting to speak. So I was just saying, so if you're planning to finalize something, maybe mean something like a land title, you'll definitely not be in a rush for it to be validated or for it to be finalized as authentic. Maybe there are certain disputes that could come in within that period, and for it to be fully on chain, maybe it picks data from some oracle that has land title information, and then later be able to mint your NFT or your your land title on chain. So until all those things have been, until nothing comes up from all those different sources where data validation is expected, the finality of that particular token, perhaps maybe NFT, should not be allowed, so that it leaves room for people who want to dispute the authenticity of that particular token to raise their fraud proofs. I hope I make sense. Like, it depends really on the use case, and actually these are things that you could consider before you decide on which blockchain you would use for your project, how they operate in the background. Does it make sense? Yes, Ronnie.
Yeah, it makes sense. But also, you talked about a time window for disputing the transactions.
Yes.
What if no one raises a claim, but the transactions are malicious?
What
How
is
are we
it?
sure that some transaction won't go through because no one has raised a claim, but they are malicious?
Yeah. I think that is the downside of optimistic rollups. That until that when I haven't actually found out what would happen later, that is something I maybe should take research on, but I would personally imagine that when the finality happens, if a fraud proof isn't raised within that window, then there's a possibility of deploying malicious information. I think that is something I will particularly look up. I'll put it into consideration. I'm not really sure what would really happen. Yeah, so can we move on? Thank you. Okay, now channels. An example, let me start with an example, and maybe someone, when you see this, you should be able to understand. You're familiar with the Bitcoin Lightning Network? Who knows the Bitcoin Lightning Network? Maybe you could help us understand it. Anyone that has some knowledge of the Bitcoin Lightning Network and perhaps how it operates? Yes, Maria, you want to say something? Maria?
Maria, I think you are on mute. I can see you're talking, but your voice is not audible.
Okay, I think maybe there was a technology glitch. So there was no one else talking about Bitcoin Lightning. Now, the way Bitcoin Lightning operates, yes.
I'm not sure, but I think it's a different network. It's like these bridged tokens, but the only thing is that for every token this side, is backed up by some other token on the main network actually.
Okay.
I'm not sure. It has some nodes there in the. I don't.
Yeah, that's actually the concept. So how it operates is, excuse me, there are tokens on the Lightning Network, but they're actually just representations of locked tokens on the mainnet, the Bitcoin mainnet. Let me give you an example of how it would look like. So, what can I use here? Miro board. I should use the Miro board. I hope it opens. This I'll just demonstrate. So, blank board. Can you all see my screen? Thumbs up, please, if you can. Thank you. So, bear with me. I'm new to this tool, so if I do something that isn't if I do something that isn't correct, you help guide me. So I'm just going to draw here. So this is perhaps person 1. Here we have person 1 here. Okay. Oops. Sorry. Let me just leave it there. So there's a person here, and there's another person there. Maybe this person has a shop. And this is a customer. Oops. This is a customer. Now, this customer maybe always does come and buy things from this shop. I think that what I'm about to explain has happened to me even in my mobile money service, and I hope you all consider thinking about a solution that can take this away. So we have a customer that buys things from this shop using Bitcoin. And what usually happens is they transact their Bitcoin and send the person to the shop Bitcoin. For every transaction they make, maybe UGX. Okay, it's a little bit disturbing. So if perhaps they were transferring 12,000, there's going to be a transaction charge on this transaction, perhaps of 3K. Imagine this, and then they have to do this maybe 4 times in a particular day, because they are coming to buy things at different times, and each time they come they are charged 3K. Let's say maybe they are buying juice. So you buy juice in the morning, you're paying with BTC, by the way. So you're paying with Bitcoin. So you're paying 12,000 worth in Bitcoin, and you're being charged 3,000 maybe as gas, I would say. You're being charged maybe 3,000 as gas. So you do this plus 4 times, times 4 times rather, sorry. times 4 times, and you have how much spent so far. That would be 24. You have 48. You have 48,000 spent in actual expenditure, and then you have how much here. You have 3 times 4, which would be which now becomes 12k in gas. So for every transaction that you're making, you're being charged 3k, and at the end of the day you spend 12,000 in gas. That is exactly 25% of your initial of your whole day's expenditure. Imagine if you're buying airtime, and in a whole day you're being charged 25% of the airtime that you bought as a payment to let me say to maybe MTN. That is a lot of money. And think about it this way: what if I could create a way of recording all the transactions that I've made in a day in a way that is trustable by the shopkeeper, and she is able to wait that I can pay that money maybe later at the end of the day, without her having to worry that I will run away with her money. Even if she didn't know me personally, what if we could create a trustless system in which she's able to trust me with her products, and I provide a proof that we've actually made this transaction, and she believes without a doubt that I will pay this money at the end of the day. Now that is exactly what channels do. So what happens is, between two people, in this instance perhaps, this person was going to pay in BTC, so they create something called a payment channel. It's just a record of transactions that are being made between these two people. It's a record of transactions that are being made between these two people. It's like a ledger. Essentially, it's just a ledger, an off-chain ledger. And by the way, this is the Lightning Network. I'm just going to use LN to represent Lightning Network. So it's just an off-chain ledger, a record of transactions. So you bought 12k, it's recorded here. You bought 12k, you bought something of 12k, it's recorded here. You bought something of 12k, it's recorded here. But for something to be valid within this ledger, within this particular, it's called a payment channel. I'm going to use C. No, sorry. Let me type it here. This is a payment channel. So for a transaction to be, how do I move it? Okay, maybe I could leave it there and give this, make it yellow. How would it be visible? Let me make it. So yeah, we have a payment channel. Now for a transaction to be recorded within this payment channel, there are calculations that are being made. So you're supposed to have you're supposed to have a token vault of a certain amount of Bitcoin on the mainnet stored somewhere with someone. So what happens is, this ledger keeps checking how much money. Okay, you've spent, the money is still here, yes, but you've spent this money and this amount of money and this amount of money. Hypothetically, there is a balance that is supposed to be deducted from the amount that you have in the vault. So maybe you had 30k, but according to the ledger, maybe you had 30k in the vault, but according to the ledger, you've already spent 20k, and you're left with 10k. Hypothetically, you're left with 10, 20 rather. Okay, you've already spent 20k, and you're left with 10. But you haven't paid this money right at the time when you made the purchase. You only gave the shopkeeper a proof of existence of that transaction, a proof of execution of that transaction. So what they hold is a proof. And then maybe at the end of the day, you make the actual shift of the money onto their Bitcoin wallet. Into their Bitcoin wallet. And the idea is to increase the transaction speed, because if all these transactions are being processed at that time when you are making the purchase, they would of course consume computing power and also infringe on the resources that could be used to process other transactions elsewhere that are being run maybe by someone else on the same network. But in this case, if you're storing just a proof, just an off-chain ledger of completion of these transactions, it's just a record. And later, maybe at the end of the day, making the actual transfer of the Bitcoin onto this person's wallet, and then eventually removing these transactions, okay, signing them as finalized, as maybe as fulfilled. Yeah, then you've completed the transaction successfully. So that is exactly how a channel works. Let me look at this. A channel, and that is how the Bitcoin Lightning Network works. It's just an off-chain ledger recording transactions between two people that have a payment channel. So now, even if these two people didn't have a payment channel, now a payment channel exists between two people. One person that will be sending, the one that will be receiving, just like the receiver could also be sending, maybe they are sending change. Because Bitcoin uses the UTXO model. So in the background, do we understand what UTXOs are? Does anyone understand what a UTXO is? Okay. Yeah, okay. So okay, what a UTXO is essentially, I hope this doesn't consume a lot of our time. So in Ethereum, if you have a balance in your wallet, okay, sorry, story is playing games on my head. In Ethereum, I'm just going to draw the logo of Ethereum here so you can see it. Yeah, maybe that's Ethereum. So in Ethereum, if you have a balance in your wallet and you make a deduction of maybe 20K, what happens is there's simply a deduction from your balance, and then the result is given here. Maybe you had 30K, maybe this was 30K, and you reduced 20K. There's simply a reduction, and you'll be left with 10K as your balance. Simple process, simple math calculation. Now what happens in Bitcoin is something slightly different. It uses a model called the UTXOs. UTXOs. It is something that hasn't been part of our main subject today, but just to explain how a payment channel could be a medium of exchange between two people. So we have BTC, and we're shifting. It uses UTXO model, and this is how it works. When you have maybe 20K, it exists in particular denominations. Just like we have cash, you may have 100,000, but it exists in different notes. Actually, UTXOs are just like digital notes. So you have 100,000, but you have 50K, 20K, and maybe another 20K, and then 10K. Or you could have 50K and 50K, or you could have only 10,000 or 20,000. It's all 100,000, but it's in different denominations. So UTXOs are just exactly the same thing. They're like different denominations that can sum up to a particular amount. So if I had maybe 20K here, it could be existing in different denominations. Maybe I have like a 5K, maybe okay, an 8K, and then a 2K. That makes it 10K, and maybe a 10K, an actual 10K. So this all sums up to 20K. And I could have a different denomination still of a total of 20K in my wallet. So what happens is, if I spent 3K from my wallet, from my Bitcoin wallet, it is going to get the 2K and consume a part of the 8K. So it sends this to the new wallet and then creates another UTXO that is a combination of 3K. So here it will give 3K and send back the 7K. So it breaks this UTXO into two, takes the 1K and leaves the 7K. So at the end of the day, I have spent 3K, but the denomination in my wallet is different. So why I brought this up is because of this. So you could have different denominations in your Bitcoin wallet. So at the time when you transfer money here, this person has to send balance back to you. Now, if you have a payment channel between you and that person, that is exactly, at the end of the day, when you make transactions to send money to them, their wallet will send, okay, even your wallet can send balance back to that person. So it's not like payment goes in one direction, it could go in the other direction as well, depending on the denominations that were in the wallet, particularly for Bitcoin and all other blockchains that use the UTXO model. So the idea of a payment channel simply is that you record transactions at a particular time and then fulfill them later. But because the Bitcoin Lightning is a decentralized blockchain, is a blockchain essentially. It is trusted, and later when transactions are finalized, of course, they will be finalized later on, but it's just an off-chain ledger. And essentially that's how it works. And it scales Bitcoin. Okay, not just Bitcoin, that's just an example of how a channel works. How it scales the base layer is, one, the transactions aren't processed in real time, and also it reduces the gas fees that are required for those transactions to be processed. I don't know if I'm making this clearer, or are we getting, or are the concepts getting difficult? Someone give me a thumbs up or ask a question. Any questions at this point? None. Okay, I hope you understand what a UTXO is at least. Okay, so now the other two
I'm wondering,
types of layer two.
finality,
Yes.
how are they sure that
How are they sure that? Yes, Ronnie. Ronnie, was it Ronnie?
Yes, I was wondering, how are they sure that the transactions, during finalizing those transactions on the minute, that the transaction fee won't be higher than they anticipated it to be? Because it can be higher, yes, yet costing them more than they expected, yet they have already cleared the other person they were doing it with.
Okay. First of all, think about it this way. If you are going to, that's why I brought this example up. If you are going to transact, if you're going to send this much money, or rather, if you're going to send 12K 4 times a day, and let me bring it up using mobile money. How much money would it require for you to withdraw 20,000? Okay, let's say 50,000. I'm just bringing up an example that will help us understand why gas fees will actually be lower for you as a user. How much money would it require for you to withdraw 50,000? No feedback? Okay, let me just explain it. So, um, if I was withdrawing 50,000, for example, it would take me maybe up to like 2,000. But if I was withdrawing, okay, there are certain, in mobile money, there are like ranges in which you can withdraw money. My point is, if you withdraw money all at once, for example, you're making one transaction, it is likely that you're going to spend less money compared to if you're making individual withdrawals of less money. Like maybe 50,000, 4 times that would be like, that's 200,000. So each of them would cost you maybe 2,000, 2,000, 2,000, 2,000. That's almost like a 10K. But if I was withdrawing to, I don't know what the actual values are, but the point is to optimize for gas. That you make one transaction that will cost you less than making smaller transactions that will cost you more in the long run. Let me go back to this example that I gave. So we had 12K with gas fees of 3K. We had maybe 48K with gas fees of 3K. This is just a total, by the way. So we did 12K at 3K 4 times. But instead of spending this 4 times a day, what if I instead spent 48K all at once in the evening? I'm just using an example of a day, and spend 3K to transfer this 48K. Which is cheaper? Would it be to spend this in real time each time you're making a purchase, or once in a single transaction where the gas fees are actually lower for that particular transaction? So this is the concept of how payment channels work. And in a sense that they, someone is saying something.
Now, I was wondering, isn't there a scenario where the gas fees will go very high such that it beats out that logic?
Mm. Now, for networks like Bitcoin, you need to understand how UTXOs operate. That's the only way it would make sense to beat out. Now, I want to show you something here. Before this is, I think this is the only way that that logic would be beaten out. But what I'm just going to show you now. So when I look at this, is a Bitcoin Explorer. Let me just zoom in. I don't want this to take us a lot of time because I want us to finish. Sorry. My internet is slowing. Why? Okay. You see, there's a transaction here. Can you see it clearly? Can you see this transaction that I just pointed at? Okay. So there's a transaction here of amount 0.7 BTC, and it's costing 25 US dollars in fees. 25 US dollars. This was 0.7. Now I want you to look at this. It was 0.7 plus $25. Then this is, I want to look for. Now this is 1.1, and it is almost the same price in gas fees as the one of 0.7. So I want us to look at these transactions both these transactions. So this chart may not be understandable, but what simply it means that this transaction was a combination of two UTXOs. There was this one and that one. When they combined, these are just distributions to the nodes, taxes to the nodes. But the transaction finalized as one block after a combination of 0.5 BTC and 0.5 BTC, these are two, combined into something close to 1. And then I look at another transaction. Please stay with me. I want to explain a certain concept that would beat the logic of a payment channel. I hope I still have that transaction here because there are many. I think this is the one we looked at. Anyway, the concept is these UTXOs are like, you can see this one has 3. So there was like one node combined with another node, combined with another digital node to form one big node. Now all these require computations. These are actual computations. Combining these 3 nodes, these 3 UTXOs, these 3 digital nodes requires computation. So the more they are, the more gas fees you would pay. Are you following? The more gas fees you would pay, you're going to find transactions that send very little money, but because they require combining of so many small nodes, there's something called Bitcoin dust. Let me actually show you something here. Let me show you the definition of Bitcoin dust. Now, can you see my screen? I want you to understand this definition before we can go back to that page. So Bitcoin dust is a small value of Bitcoins that cannot be transacted due to high cryptocurrency miner fees. So what happens is, since they can't be transacted, they are combined together into, like you'd get 50 notes, 50 shilling notes, and put them in a wallet. They'll be heavy for you to carry, even if their value would be small. So that combination of smaller Bitcoin UTXOs requires a lot of computation. So if you're making a transaction and your wallet has many of those small notes, it will be more expensive than someone that has bigger notes because they would require lesser computations for them to execute a transaction completely. So most of the Bitcoin wallets have a capability for combining UTXOs before you can transact them outwards of your wallet. But that's not something I want to go into details of. The only reason I brought this up is that if you eventually at the end of the day, if you're making a transaction from your wallet to another wallet and you have small notes, there's a possibility that you're going to spend a lot of gas fees just to make the transaction complete than someone who had bigger notes. And someone that had bigger notes, which in total would be exactly the same value. If this person had bigger notes and you had small notes, all equaling into 10K, this was 10K, and this is also 10K. This transaction will be cheaper than that transaction because this requires less computations. Just a combination of these 2 big notes. This one is a combination of so many small notes. So it will be more expensive than that transaction. Now that is the only meaningful logic that I know in which the payment channel logic would be compromised and cause you to spend more money than you anticipated. So essentially that's a payment channel. And yeah. So I think what we're left with is side chains and plasma chains. So should we go on or should we take a break and have some questions? What should we do? Some feedback, please.
I think we go on because time is about to end.
Okay, Maria is insisting we take some questions. So, okay, Maria, please ask your question. We could go on after that. Yes.
Okay. 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 For the payment channels, okay, the way you explained it, does it basically take in the opening and closing balances, or it takes in balances for every transaction, the small and then the huge? I don't know.
Okay, I get your point. Well, it takes in the closing balances for every transaction. That means in this case, if I was spending 12K, it would record 12K. Then if I was trying to record, if I was spending 12K again, it would record 12K, and again to record 12K, and again, and on the final transaction, it would record 12K. And then, according to the smart contract logic, at that particular time when I'm supposed to actually make the payment, it will transfer from my wallet that amount of money that is recorded on the ledger in the payment channel and send it to that person at a hypothetically lower gas fees compared to the 12K I would have paid if I had paid, rather the 12K in total that I would have paid if I was paying 3K in gas fees individually for each of these transactions that I made. Is your question answered? Yes, Maria, is your question answered? Somehow answered, okay. So I think we can move on. Okay, side chains work essentially like roll-ups do. They also only they have a bit of an active interaction with the parent chain. Actually, I think I should just show you a picture of that one now. Side chain for blockchain. Maybe I'll explain it when we look at it. So I think you can, when you look at this image, just zooming in it in, it's not clear. But it's like there's a constant communication back and forth between the main blockchain and the side chain itself. So now, a side chain is an independent blockchain of its own, of itself, and so is the main chain. But they have this secure data communication through something called, I think it's called a peg. I'm forgetting what it's called. It's called a peg. Yeah. Just a moment. Yeah. I think I'll find a name later, but it's just some kind of mechanism with which they communicate, the main chain and the side chain. So as they are communicating, they are transferring data between each other. They could actually have different consensus mechanisms. And what that facilitates is that when there's an overload on the blockchain or through a certain mechanism with which they communicate, certain transactions are validated on the side chain, and then the results are finalized on the main blockchain. So it's essentially like an offload layer for activity that should be going on the blockchain, the main blockchain, and then all that information is finalized. Okay, it's just an independent blockchain that can act independently but facilitates operation of the main blockchain. Yeah, essentially, I think that is it. Unless there is something I should add also, or there's some clarity I should add on it. But yeah, basically that's it. Mm, any questions up to that point? So now a plasma chain is also like an ecosystem of so many blockchains that are independent. Some of these are very, they're not very detailed. Let me just say is independent blockchain that facilitates operations of the main blockchain. So by facilitation, I'm talking things like transaction verification. Yeah, essentially transaction verification. It's a kind of thing it facilitates. Then a plasma blockchain, I'd say it's yeah, Maria had some idea about it. She actually talked about it earlier. Please help us understand what it is before a plasma blockchain. Okay, just give us your opinion of it. Yes, Maria. Okay, anyone has an idea of what a plasma blockchain is? That will be the last thing, and then we can close up. Arthur, Paul, Tracy, Ronnie, we've been very quiet. Hello?
I don't think
I'm
I've
here,
heard
but
you
I'm just
talking about that.
struggling to
Two.
to to reach you guys. You know, I've been behind a while, so
Oh,
I'm trying to cover up. So that's why
so
I'm kind of off.
so sorry about that. Now, a plasma blockchain. Let me just complete with this. It's an ecosystem. It's an ecosystem. Most of these layer 2 solutions use similar mechanisms for scaling the main blockchains. It's just that there's just a few differences in how they operate, but they're majorly doing the same thing. They're enhancing the rate at which transactions are executed and reducing gas fees for the user. It's that basic. This is how most of them operate. So, by the way, what I forgot to put here is that an example is, I'm sure you've all heard of this one. It's very common. So it's an Ethereum sidechain. It's called Matic, Polygon. Anyone's familiar with the name? A thumbs up would be helpful. Okay, so Plasma Chain is just an ecosystem of, yes?
As if I heard that the name Matic was changed to Paul,
It was changed to
something
Paul.
like that. Yeah.
Yeah, that's
Is
something
it
new.
there on CoinMarket?
On CoinMarketCap.
I think they changed it to Paul. And the
Hmm.
other thing is
Hmm.
about the side chains. Is it the same concept with the sharding? As it's
Yes, actually,
something
it's
called
sharding.
sharding.
It's like horizontal scaling. You're creating, capacity to increase speed almost at the same level. You're not maybe increasing complexity like you would say in a ZK, but you're simply expanding infrastructure. I don't know, a blockchain that I know that has been talking about it so much was Polkadot. Yeah, let me look at Polygon. Said it was changed to Pol, a pneumatic. So yeah. Anyway, thanks for the updates. I will look it up. So should we maintain this or we maintain the old one? Because just for clarity, I'll look it up anyway. And oops. Okay. So a plasma chain is just an ecosystem of chains that facilitate the parent blockchain. And this is what happens. So occasionally, maybe according to the algorithms with which they operate, they occasionally finalize their computations on the parent blockchain. And just like in optimistic rollups, also allow for disputes to be raised in a particular window. Before finality is achieved. Yeah, so essentially that is it. Let me take a look at it. It's essentially like a bigger ecosystem of side chains. And just like all other layer 2s, they deliver macro proofs. Where is plasma blockchain? See what it looks like. So here it is. Okay. I want to look at something that will help us understand it better. So it's something like this. There is a root chain, and then there are all these other blockchains serving different purposes but finalizing onto the root chain. So it's like they facilitate. Now all the transactions that would have been running through Ethereum directly, they are sequenced and run into each of these individual blockchains depending on the services that these blockchains are able to deliver. So I don't know if you've heard of things like app chains. It's like chains that are designed to process, to do certain kinds of computations. So maybe if I was running transactions on certain NFTs, this blockchain could be designed to just execute those kinds of transactions. So instead of it being run through Ethereum directly, it would be executed through this blockchain and then finality delivered on the road. So it is just it's just about enhancing the speed at which transactions are executed by the root chain, while reducing the cost of execution on the root chain. Because the root chain is expensive, considering that it has a lot of activity, and so many people want to finalize on it. So most of these are just outsources of compute to execute certain transactions. Yeah, essentially I think that is all about layer 2 solutions. Of course, there's further detail into how to implement each of them, but today we're just sharing an overview of what they are. And if there are any questions, we could answer them now, but I believe we've done a good exploration of what layer 2 solutions really look like. Not just in Ethereum, but all other blockchains. Any questions, please? maybe an example here. An example here would be, I think it's called, let me say OG. So it's a blockchain, but there are not so many of them with this kind of architecture. Let me take a look at it here. I read this somewhere. It's a payment gateway in Thailand, offline payment solutions to merchants. So this one uses the architecture. Okay, it uses the architecture of a plasma blockchain, and yeah, essentially that is it about layer 2 solutions. And if there isn't any question, I would love to end at this point and leave us to explore them further. Find examples, look at the different implementations, especially roll-ups, because I think they're the most commonly used. Yeah, thank you very much and have a wonderful evening.